Hi everyone, this is Jesse here from SkyCiv, and today we're going to be looking at another bearing capacity example. This example is going to be example 4-5 from the Bowles textbook, which takes a look at the effects of eccentricity on bearing capacity. For this design, we're going to be using the Hansen method. And the first thing I'm going to want to do is I'm just going to want to open up the bearing capacity calculator. So I can go to all calculators, for example, and search for bearing. We have three different bearing capacity tools: the Australian standard version, European standard version, and the bearing capacity version, which uses a factor of safety. And I'm going to use the factor of safety version because the design examples also use a factor of safety approach. Now that I have that tool open, I'm just going to look at inputting the values from the design example. So we're going to be using the Hansen method. We have a rectangular foundation, and we're going to be assessing the drained analysis case. For our dimensions, we're told we have a square footing. It's 1.8 by 1.8, and it's also 1.8 meters deep. So I can update that and see that reflected in our drawing. We're told that the soil parameters are a cohesion of 20 kPa and a friction angle of 36 degrees with a unit weight of 18 kilonewtons per meter cubes, and a water table depth of 6.1, which is deep enough that that's not going to impact our unit weight. We're also told that for design loads, we have a 1800 kilonewton load. The design case that we assign is not going to matter because it's not going to be factored in this calculator. And we're told that we have two moments. We have a moment about x of 450 kilonewton meters and a moment about y of 360 kilonewton meters. Because we have the square footing, it's a bit almost arbitrary about which direction we put it in. But we're going to see in the calculator what happens with these two values and if they should have been switched. We're also told we're going to be using a bearing safety factor of 3. And with that, we have all our inputs the same as Bowles example 4-5. Now we can go through this calculator and compare to the results from the textbook. So first of all, let's just scroll through and look at the start of our calculations. Now this is the most important part of calculations when we're talking about eccentricity effects. It's the calculation for our effective foundation dimensions. And the way this calculation works is we get an eccentricity using the moment about our foundation in each direction. So we have an eccentricity in the B direction, an eccentricity in the L direction. And for this, we just use the moment divided by our axial force. And from these calculations, what we end up with is these two dimensions: B dash, the effective width, and L dash, the effective length. Now what we'll notice here is that actually the way that I've input these moments, because the moment about the B axis is larger than the moment about the L axis, the effective length is actually shorter than the effective width. So in reality, I probably should have put the loads in the other direction for this square footing. But regardless, when you input your loads, what you'll find is if we ever have an L dash that is less than a B dash for this calculation, we're just going to switch those two values around so that we're actually making sure we're always checking the conservative direction and using the smaller value in our design. So here we can just see that we've switched the directions for B dash and L dash going forward. But if we put in the load table these loads switched about, we just wouldn't have this because we wouldn't need to switch those values in the first place. If we had input these moments differently, opposite way, we would have B dash equals 1.3 and L dash equals 1.4 already, so we wouldn't switch those. But regardless, we've got the dimensions now, and we're going to use these dimensions in our design. So that's how we deal with having moments on our foundation. We just use these effective dimensions, and then we do the calculations as if we didn't have any moments at all. As we scroll through, we can get to the Hansen bearing capacity calculations. First thing we do is calculate the bearing capacity factors. This calculation is slightly different to other methods, giving us slightly different parameters we might have for Tazagi, for instance. We calculate inclination factors. In this case, we don't have any horizontal loads, so inclination factors are all just 1. We calculate our shape factors. Now note that for the shape factors, we're using the effective dimensions to get a conservative result. But for the depth factors, when we do our calculation, we're using the actual value, 1.8. And you can see the reason for that is that B is the denominator term. So if this is larger, we'll get a smaller depth factor and a more conservative result. And this is just recommended in general when we're using this method for how to calculate these factors. For ground factor, base factor, both are just 1 because we don't have any inclination in our grounds. And finally, we can get a summary of all these factors. There's many factors that we've calculated, most of which are just 1 anyway. And we can combine all these factors to get our final results. Now, looking here in the calculations, I can see that the dimensions, the effective dimensions used in poles is 1.3 meters and 1.4 meters, as we've discussed. And they calculate the shape factors all very similarly, and all the other factors very similarly, but we can just look at the end result and compare that to see if we're getting a similar result. And the final result that they get is 5,090 kPa. So it's very similar. There's probably just some rounding differences there. The components that they have are all quite similar for these 3 different terms. Again, it's just rounding differences on some of these factors that can result in, some differences in the end result, which is what we see when we compare to that textbook. And when we divide by 3 our safety of factor, we get 1690 kPa. They're using 1700 kPa with just rounding being applied, which is ultimately a very similar result, only with differences due to rounding. So we can see we're getting the same result as the Bell's textbook for this design example, and we can see how easy it was to input all these values, run this result, and get a very comprehensive design report. So thank you for watching this video. I hope this helps you to learn about how to calculate bearing capacity when dealing with eccentricity. If you have any questions about this design example or any of the other videos in the series, you can message me here or message the team here. Otherwise, I'd recommend you just play around with this tool and play around with other quick design tools in our library. Thank you for watching this video. Bye.